I'm Cameron Wolfe. If you're wondering why I put the R in between my first and last name, I'm not trying to be pretentious. There's actually a super famous Cameron Wolfe out of Duke who does like medical research. So I have to differentiate myself for Google Scholar and stuff. But I'm a research scientist at Alegion. It's a startup company based out of Austin, Texas. We do data labeling for video data. We're the industry leader in that space. So if you're interested, check it out. But I'm also a PhD student at Rice University in Houston, Texas. And that's kind of where most of the work that I'll be talking about today comes from. So the topic of the presentation today is just hyperparameter scheduling for computer vision. And I really like this topic because it's very simple. You can get a lot of practical takeaways from it, and it makes a big difference in the things that you'll do day to day as a data scientist or a machine learning engineer. So hopefully the goal of this presentation is to just present some simple stuff that makes sense that you can kind of take away and use in your day-to-day life. So this talk at a high level is just about how to properly train a neural network. More specifically, we know that in a lot of cases, maybe a little bit more for NLP at this point, given all the LLM stuff, but deep learning can still be pretty computationally expensive for computer vision. And proper hyperparameter tuning when you're training a computer vision model is extremely important. And to understand why this is, we can kind of look at what a typical deep learning setup will look like. So we have our neural network. This could be vision transformer, CNN, whatever. We have some kind of optimizer. We have our data set that we're training over, so just a bunch of images. And then we select our hyperparameters and kind of kick off the training process. So you're going to go through all of this data for multiple epochs. And the goal is that eventually you'll get a good model. But there's kind of this extra step of checking whether your model performs well at the end of this training process. And if it doesn't, then you have to go back to stage one. And we're kind of in this continual loop where if we don't select our hyperparameters properly, we're continually retraining our network, trying to get one that performs well. So while most people look at the computational expense of deep learning and say, this is just because we're training over big data sets and our models are large, this problem is true, but it gets a lot worse if we choose our hyperparameters incorrectly, because we have to incur the expense of training our deep neural network 2, 3, 4 times and so forth. So the idea here is that we want to try and get some practical takeaways for hyperparameters, how to set them properly, and more specifically, how to use hyperparameter schedules, which recently have become like super popular for deep learning and computer vision. So you could think of, for example, learning rate schedules, where for computer vision, you have things that are just widely used like step schedules or cosine annealing schedules, things like this. So that's the purpose of the talk. It's just figuring out what are hyperparameter schedules and how can we set them properly so that we don't have to continue tuning our neural network over and over again. So we'll go into 3 spaces in particular. The first is for the learning rate. The second will be for training precision, which is a little less known to some people. And then the third will be video deep learning. So we'll start out with the learning rate just because it's probably the most easy to understand and a topic that pretty much anybody can take away and use as a deep learning practitioner. So the work in particular that we'll be overviewing here is a paper that I wrote with Rice. It's called REX. And the idea behind it is that when we consider different budget settings for training a deep neural network, certain learning rate schedules actually work better than others. So this portion of the talk will be focused on that particular topic. But if you scan the QR code, I linked to a blog post in one of the links at that QR code. Basically, that will go over a bunch of other practical learning rate takeaways that you could use in general. But today we'll be kind of focusing on this work that I did. So the idea behind REX is that when you're training a CNN or whatever type of deep learning model, you oftentimes have some type of compute budget. Maybe you're working for a startup and it's a monetary budget where you don't have to spend too much money. Maybe you're trying to meet a deadline for work, so you know that you can't spend too much time training your network. But at the end of the day, one of the most effective ways for meeting a budget like this, and it's actually been shown recently to be a very hard baseline to beat, it's just simply reducing the number of training epochs that you're doing. So instead of training a model for 200 epochs on ImageNet, you can shorten it down to 90 or something like this, and you can probably get pretty good performance if you set your hyperparameters correctly. But when we reduce the number of epochs, we kind of have 2 options for what we do with the rest of our training process. One would be to just leave the training setup the same. So we use all the same hyperparameters and settings as if we're training for the full number of epochs. But unfortunately, this doesn't work well a lot of the time. So what we have to do is actually find a better budget-aware training setup for these low budget settings. So that's what this work focuses upon. It's basically looking at training neural networks for shorter numbers of epochs than they would usually be trained for, and trying to figure out how to do this properly, particularly how to set our learning rate. So what are the best practices for hyperparameter schedules for your learning rate when you are operating in a budget-aware setting? So to explore different learning rate options for this setting, we kind of decompose learning rate schedules into two components. The first component is a profile, and this is just the function that kind of models the decay of your learning rate. So a very popular one would be cosine. A lot of people use the cosine function to decay the learning rate, but you could also use a linear function, exponential. Step schedules actually follow an exponential function. But yeah, you choose your profile, and that's the function or the shape according to which you anneal your learning rate. And then the other component would be the sampling rate, which simply just tells you how frequently you want to update your learning rate. And this might be a bit difficult to understand compared to the profile, so I'll kind of show an example of how this works. So if we take a linear schedule in this right subplot, for example, we have our profile, which is just a linear decay profile. But we can actually choose different sampling rates along this profile. And here we see that, for example, if we use a 50-75 sampling rate, meaning that we update the learning rate 50% of the way and 75% of the way through training, we see that we're still kind of going, decaying according to this linear profile, but we're only changing our learning rate those 2 times during training. So we get something that kind of mimics a step schedule. But really, if you think about most fixed learning rate schedules, this might not include things like decay on plateau or more exotic strategies, but most fixed learning rate schedules can be defined in this way by just taking a profile and then defining a sampling rate. If we have some kind of fixed learning rate schedule, we can probably define it in this way. And the contribution of this work is basically introducing a new profile for learning rate decay, which we call reverse exponential, or REX. And REX, you can see it in this right subplot here. It's basically just a learning rate schedule that will keep the learning rate high for a while and then decay it to a lower learning rate at the end of training. So instead of doing something like cosine decay or linear decay, where you kind of reduce the learning rate smoothly throughout training, REX kind of waits longer to reduce the learning rate and then decays it a lot at the end. And what we do is we basically, for each profile, find the optimal sampling rate across a bunch of different domains. Most of these are in the computer vision domain, so you can see everything except for BERT-based as a computer vision experiment. We test generative models, classification, object detection, so forth. So lots of different computer vision domains. And then we take these optimal profile and sampling rate comparings and see how they perform and compare them to several different popular learning rate strategies. So in particular, we have 6 different learning rate schedules that we test. They're shown in this figure on the upper right here. So just different popular learning rate schedules that you might see throughout deep learning research. And what we do is take all of these schedules, test them using both ATOM and SGDM, and then across all of the domains, we aggregate the results or the performance of these models across all of the domains. So the way that we do this is basically test if a single learning rate schedule is the best performing schedule out of all the other variants. So in this table at the bottom, consider, for example, if we ran 4 different settings and then the REX learning rate schedule performed the best 3 out of the 4 times, then we would report a top one of 75%, because in 3 out of the 4 trials, REX was the best performing learning rate schedule. So this table at the bottom just takes all of these different domains that we tested and sees how many times do each of these learning rate schedules achieve the best performance or in the top 3 of the best performing learning rate schedules. And what we see when we aggregate all of these results are a couple of interesting findings. First of all, which is especially relevant to computer vision, step schedules only perform well in the high budget regime. So step schedules, or you could think of this as just starting with a high learning rate and then decaying it at 2 or 3 points during training by 10x. they're commonly used in computer vision, typically going to be a default for a bunch of different GitHub repos that you would see. But what we see here is that step schedules only perform well if you're using the specified large number of epochs. If you reduce the number of epochs that you're training for, they actually aren't the best strategy to go with, or they deteriorate a lot in their performance. Additionally, we see that Rex actually performs really well across domains and budgets. So we can see across both low budget regimes, so training for a low number of epochs, and high budget, or just the normal number of epochs that you would train for, Rex performs really consistently, tending to achieve the top one performance 70+% of the time. So what we can kind of take away from this is that everybody sets learning rate schedules, but the correct way to do it might depend a lot on what budget that we're using, right? So many choices exist for our learning rate schedules. A lot of the best learning rate schedules are probably dependent upon the exact settings. So if you reduce the number of epochs, maybe one learning rate schedule doesn't perform as well. Additionally, if you change to a different domain or a problem, like go from image classification to object detection, maybe the best learning rate schedule changes. But across all of these domains and settings, Rex seems to be really easy to use, and it performs well across all of the settings. So it's just a consistent learning rate schedule that you can adopt, and it's really easy to implement. So as I said, this part of the talk focuses on Rex just because it's a paper that I wrote. But if you scan the QR code, there's a link on that page that says presentation links. It also links to an overview that I wrote of just a bunch of different useful strategies for your learning rate. So you can check that out if you're interested in other stuff like cyclical learning rates, warm-up periods for learning rates. It also links to a GitHub repo with implementations of a bunch of common learning rate schedules that you can use if you don't want to implement it yourself. So yeah, that's the learning rate part of the talk. If anybody wants to ask any questions, feel free, since it's probably good to pause in between sections. Any comments on Rex in regards to transfer learning? Yeah, that's interesting. We didn't test that in this case, but that would be a really interesting test to run. A lot of times what I've found is that when you're fine-tuning a network on a downstream data set or something like that, if you start with too high of a learning rate, that might cause problems. So my guess would be that Rex is fine for transfer learning, but you have to be careful with setting the initial learning rate to make sure that it's not too high. But again, that would be pretty cool to test. So let me know if you try it and find any problems with it. In addition to domain and budget, do you see that just the data set itself, size diversity, can cause one LR to work better or worse? Yeah, so typically I would say that all of these things are kind of factors that you have to consider when choosing hyperparameters. So we can kind of boil this down to the question of, if you're training a neural network on one data set and you kind of switch it and try to train it on another data set, are you going to just use the same hyperparameters out of the box? Probably not. You're probably going to have to test a few things and see what works. So always, it's a bad idea to kind of just use hyperparameters that you're using directly when you change domains or data sets or something like this. Probably you're going to have to do some more tuning or figure out what the best thing to use for your new data set is. When do you think we'll see convex optimizers for arbitrary neural networks? I'm not 100% sure what that means. I mean, neural networks, like by nature, are non-convex, but at the same time, you know, I mean, a lot of even though neural networks the optimization problem is non-convex, a lot of optimization algorithms, all of the proofs are in convex settings or kind of simplified settings. The literature for analyzing like non-convex convergence rates is a lot harder than like the convex proofs. So typically it seems like for deep learning, we can kind of take intuitions from convex optimization and see whether they'll work. And in the case of like SGD and stuff that we use today, it works really well. So yeah, hopefully that answers the question. Then how are we initiating Rex? So basically, like all Rex is that you choose an initial learning rate, you have a schedule by which that learning rate is varied, and then from the beginning to the end of your training, you decay the learning rate from the initial choice to kind of 10x lower than that initial choice, or maybe 100x according to that schedule. So there's no initiation needed. It's really just a fixed function profile by which we decay our learning rate. And in addition to randomizing training sets, do you insert initial disturbances? So no, really all we do here is just pick a bunch of different domains, bunch of different publicly available data sets, and then run training across all of these to see which learning rate schedules work best. So all of the setups are like pretty standard, I would say. We're not doing anything extra, just running training over public data sets. Cool. So that seems like the last question for now, but I'll pause at the end of each section. So feel free to ask questions. If you have something else come up, I'll answer it at the end of this section as well. So the next area that we're going to talk about is training precision. This might be a little bit less familiar to some people, but I think it's super cool. So probably worth covering. The idea here is that we're kind of doing low precision training for neural networks. So instead of training your neural network at the normal 32-bit precision, we're lowering this to something like 16, 8 bits, maybe even lower. And when we perform all of the arithmetic of the neural network in these lower precisions, we can save compute costs, right? So in particular for this paper, we're looking at cyclical precision training, which means that we're kind of varying the precision that we're using for our neural network cyclically throughout the entire training process. And we'll find that that can yield a lot of performance and training efficiency benefits. So little motivation on how this works, since I know maybe this is a little bit less familiar compared to something like setting your learning rate. But again, training deep neural networks is computationally expensive. We want to find ways to make this less so. And one of the most popular things to do right now is low precision training, because you can get compute efficiency and oftentimes not damage your model's performance or even make it better. And the idea of how this works is shown in the figure on the right here. This is an arbitrary kind of just like neural network diagram. Maybe there are a few more bells and whistles when you implement it for something more complex like a CNN. But the basic idea is that we're just, when we do our forward pass, we're taking our activation and our weights, and we're quantizing them to a lower precision before we perform the matrix multiplication in the forward pass. So because of this, our forward pass matrix multiplication is at a lower precision, which is faster. So we get compute savings, right? So we're doing the same thing that we do normally with neural networks, but just doing it in low precision. We do the same exact thing for the backward pass. The only difference is that there's 2 matrix multiplications in the backward pass, one to compute your weight update and one to propagate the gradient to the previous layer. So we actually save twice as much compute. But this is the idea here. We're just doing everything normally, but for the matrix multiplications, we're quantizing the activations of the gradients as well as the weights so that all of these operations are actually more efficient than before. And there's a bunch of papers that studied doing fixed low precision training techniques. So you take something like 6 bits or 8 bits and say, we're going to adopt this fixed precision level and train our neural network throughout the entire number of epochs using this precision, which worked well. But then people published papers after that and said you can actually cycle your precision throughout training and save even more compute. So you take the fixed level, 8 bits, 6 bits, whatever it is, and then you cycle your precision below this fixed level throughout training, which makes you save even more compute costs, right? So we see that via cyclical precision training, CPT, we can train neural networks even faster. So the question we're going to ask, and the paper that I'm actively working on right now, is that people have already proposed CPT. They actually used cyclical cosine schedules for CPT, but they didn't test any other types of hyperparameter schedules. So linear schedules, rect schedules, exponential schedules, they just did cosine and didn't compare it to all of the other alternatives. So we're going to take a bunch of different schedule options and see if we can gain anything out of exploring these alternative hyperparameter schedules. So in particular, how we do this is we follow a similar approach to Rex and kind of decompose our precision schedules into 3 parts. One would be selecting a profile. This is the same as Rex. We consider several different profiles, the cosine schedule, the linear, exponential, and Rex. We kind of argue based on this left subfigure here that it's pretty comprehensive in terms of the behaviors that you would want to get out of your precision schedule. So we only consider these 4. After this, we select the number of cycles for your precision that you're going to perform during training. So in the right subfigure here, we can see 1 cycle, 2, and 4. Really, all that this is doing is it's just repeating the schedule that you're following multiple times during the training process. So hopefully that's pretty easy to understand. And then the harder part is choosing repeated or triangular schedules. So first of all, notably, you'll see that we don't have a sampling rate here. This is because for the precision level that we're setting during training, we always have to round it to the nearest integer. We can't perform a multiplication with 4.5 bits. It has to be 4 or 5, right? So we're always rounding precision to the nearest integer, and that kind of tends to control the sampling rate. We can't update our precision as fast as like the learning rate because we have to round it to the nearest integer. So we don't consider a sampling rate here. But to better understand what we mean by repeated or triangular schedules, I'll show you the set of precision schedules that we end up with. There are 10 of them, so we can see them all in this figure here. For an example of what a repeated or triangular schedule looks like, we can look at the top left subfigure here. So linear repeated schedule, we're really just starting from a low precision and growing up to a higher precision, and we do this over and over again during training. Differently than the learning rate, we actually want to end always at a high precision. This is because lower precisions introduce noise, so they're not good for the model converging. So always during training, we kind of, if we're varying our precision, we want to end with a high precision. So that's a repeated schedule. We just do the same thing over and over again. If we want a triangular schedule, we see something like on the top right subfigure here. So instead of just repeating the same linear growth schedule over and over again, we reflect one of these growth schedules so that we decay our precision and then grow it back up. So you can see these triangular schedules a lot for learning rate or different hyperparameters, but it basically just, instead of using the same profile over and over again, you reflect one of them so that you're going up and down in an alternating cycle. The only extra complication to this is that if we define a triangular schedule as just reflecting one of your profiles, for profiles like Rex or exponential profiles, there are 2 different ways that we could reflect it, horizontally or vertically. So if we consider those 2 different triangular reflections, the 4 profiles, then we end up with these 10 CPT schedules shown here. So these are all the precision schedules that we test. You can kind of see that they should characterize a pretty broad scope of different precision scheduling behaviors. So what we're going to do is take all of these schedules and then test them across a variety of computer vision domains to see if we can get anything by using more exotic precision schedules. And we actually divide these into a couple of groups. The reason that we do this is that, unlike the learning rate, your precision schedule doesn't just impact your performance, it impacts the amount of compute savings that you're having. So if we use a linear repeated schedule, it will provide a medium amount of compute savings, but Rex schedules, for example, they cut compute costs down a lot more, right? So precision scheduling is pretty interesting in that it impacts the network's performance, but also the type of schedule that we choose will dictate how much compute savings that we get. So we kind of divide them into a couple of groups based on their kind of general level of compute savings that they'll provide. And what we get at the end of this is this super complicated figure here. Basically, on the bottom here, we have the effective number of bit operations. So this is similar to flops, but throughout your entire training process. This characterizes compute efficiency, where a lower score is better. So lower score indicates less compute. And even though this figure is very complicated, we can kind of just look at a few things that stand out. First of all, when we look at all of these different precision schedules, what we'll see is that there tends to be a correlation between the model performance and the amount of training compute that we're using. So if we use less compute or have more computational savings, we tend to get a little bit worse performance and vice versa. So even though we can use these alternative precision schedules, in a lot of cases, we're not getting these compute benefits for free. If we want our training to go by faster, we're probably going to get a model that performs not quite as good. This isn't always true, but in general, we see that there tends to be a correlation between the amount of compute and the model performance when you consider all of these different precision schedules. Additionally, we see that in certain cases, using alternative schedules, so stuff beyond just cosine schedules, can actually be really beneficial. So here, for example, for training a ResNet 18 on ImageNet, we see that using cosine schedules or other schedules that have similar amounts of computational savings kind of performs similarly to the baseline, which is a fixed precision training strategy, just the star right here. But the best performance actually comes with the rec schedule. So, or exponential schedule, sorry. Basically what we see is that if we test some of these alternative schedules, we can still save compute costs, but actually perform better than these static precision baseline techniques, right? So by exploring stuff beyond just cosine precision schedules, we can get a lot of different benefits. And then, which might be kind of intuitively something you'd expect, in certain settings, if we perform too much quantization, so if we're using precision levels throughout training that are way too low, we're going to get a performance detriment because some settings are more sensitive to the lower precision levels. So you can't always train a network with really low precision, kind of depends on the domain. Here we see that training on larger scale data sets like ImageNet tends to kind of cause problems. So you have to be a little bit careful with how low of precision you're going to be training with. But at the end of the day, what we find with this work is that you can just gain a lot by exploring alternative hyperparameter schedules for cyclic precision training. If you have to choose one, basically what we recommend is that small schedules, so the ones that provide the most computational savings, are good for minimizing training cost. If you want to maximize your model performance, you should use one of the schedules that doesn't lower the precision quite as much. We see that as you kind of use those schedules, the performance will get better, even though you get a little bit less of computational savings. And then if you want your model to perform well, but you want efficiency too, then maybe just choose something in the middle. So choose the schedules that will perform low precision training, give you like reasonable compute savings, but also maintain good performance. Notably, now that we understand like all of these different precision schedules, is something to note that's pretty important is that none of these can actually be used practically right now. That's because current hardware, NVIDIA GPUs, they'll only support low precision training at certain levels. So I think right now the lowest level is 16-bit, though maybe it's a bit out of date, but we can't support arbitrary precision arithmetic on GPUs, right? So we can't perform 4, 5, 6-bit arithmetic. So the best thing to use for low precision training right now is just something called Apex, which just implements 16-bit precision training without having to change your code in PyTorch or whatever. You can train models twice as fast without really having any performance detriments. So if you scan the QR code, again, at the presentation links, I linked to an overview that I wrote of quantized training, and it talks about Apex in there and how you can use it. So if you want to use low precision training, that's one good option that exists right now. But hopefully hardware engineering will catch up with this research so that we can use more exotic low precision training schedules like this in the future. So now we've covered learning rate and training precision. I'll stop for a minute to take a few questions before we go on to the last one. Let's see. Low precision training, is that also called quantization aware training? So I think quantization aware training is a little bit different. And the reason for that is that I think quantization aware training refers to the particular case where you're training a neural network and you want to quantize it at the end of the training process so that you can deploy it onto an edge device or something like this. So the purpose of that is training the network in a way that when you quantize it, it will still perform well. So when you convert it to a low precision representation that uses less memory and so forth so that you can deploy it. The difference between that and what I'm doing here is that cyclical precision training and stuff that's similar to that, it's not focused on trying to create a smaller neural network at the end. It's focused upon trying to reduce training costs in general. So we're actually performing the training process in a low precision manner so that we can save compute costs during training. We're not necessarily trying to quantize the network to make it smaller at the end. Though whether there's a relationship between like this low precision training and quantization aware training, it could be that like performing low precision training like this is a good method of quantization aware training to where these networks are easier to quantize at the end. I'm not sure, but in this case, quantization aware training, it's really just methods that make your network perform better when you make it smaller at the end. Is CPT theoretical, implemented entirely in software? Yeah. So as I said, like there's not hardware support for this yet. I still think it's like kind of cool, and I hope that hardware will catch up with it eventually. But right now, the best thing to use is Apex, because you can train at, floating point 16 precision. You probably won't lose any performance, though check to make sure, and it'll be about twice as fast, maybe not quite that much, but it's a pretty good speed up, and it's very easy to implement. So definitely use Apex. Are there trade-offs, disadvantages from low training precision? Yes, for sure. So when we saw like the graph before, so let me take a look at here. Basically, sorry. So what we'll see is that there's a correlation between model performance and training compute. So if you're lowering the precision too much, you're going to pay the cost. Your network is going to start kind of deteriorating in performance. This is relative to just training with a fixed but lower precision level. But if you kind of adopt a different strategy that doesn't quantize quite as aggressively, you might actually improve model performance while saving compute. So we can see that, for example, with this ImageNet case, compared to the baselines, the exponential precision schedules, they both reduce compute compared to baselines and improve the performance. So it depends. There is a trade-off if you quantize too much, but there are certain cases where you can actually get better performance and save training costs. It just depends on the scenario. FYI, GSI technology has ASIC custom hardware that supports arbitrary bit precision programming. That's awesome. Yeah, send a link to people if you can, because that would be really cool. I think that once this tech kind of works well in hardware, it will actually be pretty useful practically, but we'll see how quickly, the kind of mainstream hardware can catch up with that. Cool. So last topic here is the only one that I haven't done research on, but I kind of included it just because I thought it was a really cool application, and that's video deep learning. And I'll try and give a little bit of background to take people who have only experienced image CNNs to a place where they can understand kind of how these similar networks work for video. So the idea here is that we're just going to cycle the batch size that we're using for our video CNN, and then we're going to do that in a smart way that will speed up the wall clock training time of this network. So the first question that we're going to ask here, probably there's a lot of people who have never dealt with video CNNs. This is because they're more expensive to train. So kind of the barrier to entry is higher than just training CNNs over images and stuff like this. But they're not super complicated. Basically, the only difference is that we take a 2D convolution that you see within our CNNs for images, which just has a 2D convolutional kernel that we convolve over our input or our features, and we add an extra dimension to this. So this dimension in particular corresponds to the time dimension. So each video is decomposed into frames. Basically, each frame is probably going to be an RGB image or something like this. But if we order those frames properly, we get images that move through time, which is a video, right? So videos aren't much different than images. It's just a bunch of images that are temporally ordered to create motion information, right? So if we want to take a 2D convolutional kernel and generalize this to a video, all we do is that we take this 2D convolutional kernel and add an extra dimension to it so that the convolutional kernel considers spatial information, so within one frame, but it also spans multiple frames. So instead of just stepping this kernel through our image, convolving it, we step the kernel through the image spatially, but at the same time, we're convolving temporally or stepping through frames. So really, the idea of a convolution is still exactly the same. We're just accounting for the fact that we have multiple frames within each input, not just a single image. So when people first considered this question of how can we take, 2D CNNs work really well, we have all these awesome results with AlexNet or whatever that came out in the mid-2010s. We want to take this and apply this to video. How do we do this? The first thing that people encountered is kind of a lot of bad performance and frustration. And the reason for this is that we had models that had a lot of parameters. So this is because when you take a 2D convolution and extend it through time, the number of parameters increases a lot, and we don't have as much data. And the reason for this, and we encounter this very frequently at Alegion because we do a lot of video annotation, Videos are very hard to annotate unless you like do your UI very well. So the problem here, we have these massive 3D CNNs. We don't have a lot of data. So all of these networks overfit and perform poorly. And basically handcrafted features were a lot better. So the state of the art for a long time was just using handcrafted features that you can extract from video, passing those to SVMs and so forth, similar to the approaches that we used before deep neural networks for image classification. And even though these networks didn't perform well, they're very computationally expensive to use. So for a long time, video deep learning lagged behind image deep learning just because of all these complications. This was kind of improved as we got to some better network architectures. So it's a combination of better network architectures and having bigger data sets, but both of them were kind of necessary. So the one that we'll be considering in particular for this paper is something called a slow fast network. And basically what this network does is instead of having just a single 3D CNN that we convolve over the entire input video over multiple layers, we separate our network into two different modules. Each of these modules are 3D CNNs, but they're kind of in charge of capturing different kinds of information within our input video. So the first 3D CNN is the slow pathway, and this is in charge of capturing spatial or semantic features. And then we have another 3D CNN that's in charge of capturing motion features. And the idea of why we would want to make this separation is that these features in video are kind of very different from each other. So when we think about semantic features, whether an object within this video is a dog is not going to change very quickly frame to frame. So we have a dog in one frame, very likely to be a dog in the next frame, right? So we're not getting very high frequency changes in these kind of semantic features, but motion features are the exact opposite. So if an object is moving very quickly, the position in the next frame could be very different than the current frame. So what we do to kind of create a network architecture that can handle this kind of difference between temporal and spatial information is separated into these two pathways. So the slow pathway, we pass our input as a low frame rate. So we take the underlying video and we sample the number of frames that we pass to the neural network way more sparsely. And this provides computational benefits, obviously, because we're passing fewer frames as input, so the compute expense is lower. Alternatively, for the fast pathway, we have a very high frame rate. So this is trying to capture the motion information. So we have very dense sampling of frames that we pass to the network, but we reduce the number of channels in the network very significantly so that we don't pay the compute cost of all of these frames. So here we're just separated into two separate modules. Slow pathway considers very few frames as input, so this reduces compute expense. And then the fast pathway reduces the number of channels significantly so that we don't have a massive computational cost if we have a bunch of frames as input. So in aggregate, what we get is just a network that is very efficient to train because we separate capturing semantic and spatial features and do it in a way that can actually reduce compute costs a lot compared to normal 3D CNNs. So this network performed really well, and it also saved a lot of compute costs. So moving on to hyperparameter schedules, trying to draw a connection to what we've been talking about for the rest of this talk, video deep learning models, in addition, we saw this with the other models that we've overviewed, but video deep learning models especially are very expensive to train. This is because when we consider video data, depending on the FPS, but it's generally an order of magnitude increase in the amount of data that we have to consider, because instead of just dealing with a single image, for an example, we have a video which could be 10 or even 100 images associated with our input, right? So the amount of data we're considering increases by an order of magnitude. So we're trying to find ways to make these models much faster to train because they're so expensive to train to start out with. And one way that we can do this is kind of look at the mini batch size that we use for video deep learning models. And if we look at the figure at the bottom here, the mini batch for a video deep learning model has one more dimension compared to a normal mini batch, right? So our batch size is just the number of videos that we're passing to our model. But beyond that, we have another dimension that's basically how many frames do we consider within each video? And then for each of those frames, how wide and tall is the image? So here the added dimension is just the clip length, right? So for a normal image batch size, we're going to have several images with certain width and height. Here we have the same thing, but each example has several frames within a clip. So we have a 4-dimensional mini batch. And what we have to choose is the resolution of this mini batch. So if we use a higher resolution, so lots of frames, very wide and tall images, we may get good performance, but this is a larger input that's going to be slower to train. Similarly, we could go with low resolution, where we sample very few frames per video, have smaller images, but even though this is fast, it'll probably perform poorly. So the question here is, how do we set the mini batch shape if we're trying to train efficiently but still get good performance? And the answer that's proposed by the paper that we're looking at, it's called multigrid training methods, is basically to not choose a single mini batch size, but vary it according to a hyperparameter schedule. So you'll see here that basically there are different fixed levels or sizes of mini batches that they'll use. These are chosen according to which mini batch sizes fit best in hardware to maximize efficiency, but they use these different fixed levels of mini batch sizes and they cycle between all of these different levels. And what they find is that this performs way better than just normal training with a single mini batch size. So in comparison to just training normally, we get models 4.5 times faster than before. So we see that basically just by adopting this simple approach, we get a massive improvement in the efficiency of these models with no deterioration in performance. So in particular, we can look at this result on the right, which is training over a kinetics data set, which is a kind of just the ImageNet of video classification. And what we see is that if we're training on a single GPU using this multigrid training method, which is just cycling the batch size for the video model throughout training, we can get the same top one performance and achieve this in 2 days on a single GPU instead of like an entire week. So this is a pretty massive improvement in the efficiency of these models. And what this tells us more or less, like, yes, you know, cycling the batch sizes is great for training slow, fast networks more efficiently. But really my point in including this is that hyperparameter schedules aren't just for your learning rate. So as we've seen within this presentation, we covered stuff about the learning rate. That's very cool, but this is more of a fundamental concept in deep learning in general, right? So we can use it for things like precision. We see that this provides a lot of benefits. And then even in cases like cycling our batch sizes for video, you know, 3D CNNs, they end up being useful. So hyperparameter schedules are a really fundamental concept. And I find these works really interesting because you can apply them in a bunch of different places and they end up being useful a lot of the time. So that's the whole presentation. We've gone over the learning rate, talked about Rex. Basically, the idea of that is that if you're in a low budget setting, using the Rex learning rate schedule might be a good idea. We talked about training in low precision. If you want to use it practically, use Apex. But there's a lot of work and research beyond that right now that's interesting that can cycle precision to theoretically save more compute costs. And then in video deep learning, we saw that hyperparameter schedules aren't just for learning rate and kind of normal things that you could see. They apply to pretty much anything in deep learning. You can use them in a bunch of interesting places and find a benefit. So I'm glad to take some questions. This QR code, I write like a newsletter, which a bunch of just paper summaries and stuff. So if you want to follow it, go to it. But this just links to stuff for the presentation and anything for connecting with me if you're interested. So thank you everybody so much for listening to the talk. Hope it was useful. Please ask any questions if you have some.